Hey folks, happy Friday. Today, I suppose no one else is around. Today, we are going to be doing a specific heat capacity lab. So I'm getting that set up right now. You can tell I have a hot plate here, obviously, and you can see it's just starting to bubble a little bit with the water. The goal of today's lab is going to be to calculate the specific heat capacity of 4 unknown samples of metal. Now, the way we're going to do this is sorry about that. We have these little bundles of metal that I have kind of wrapped up with fishing wire or fishing line, and I have 4 different types of metal. All right, this is unknown sample A. Okay, really heavy, really dense stuff. This is unknown sample B. Okay, I'll show you the other side. Okay, lighter, substantially less dense than this first one. Both obviously silver in color. Unknown sample C is this. You can tell it's all kind of rusty. Okay, a little more dense than the second one, not quite as dense as the third one. And then I have sample D. Again, kind of silvery, kind of grayish looking, and I'd say like on the lower end of density maybe. So anyway, so I have these 4 samples of metal, A, B, C, D, and what we're going to do is we're going to have a heat transfer occur. Okay, I'm going to have a heat transfer occur between these metals and some water. Now, we're going to have this heat transfer happen in what I'm going to call a coffee cup calorimeter. Now, that sounds kind of lame, but a coffee cup calorimeter is styrofoam cups with a lid on it, which we will cap and transfer the heat. So let me kind of give you a rundown of the math that we're going to be up to today. What we need to do today for math is we're going to have to use our Q equals mc delta T equation. And we're going to have to do it twice for each trial. Because what we're going to do, and the reason why I'm heating up this water over here, is eventually when this is boiling, okay, I'm going to take my metal sample, and this is why I have the fishing line, by the way, okay, so I can actually, hold on to it. But I'm going to take my metal sample, and I'm going to submerge it in the water and let it reach thermal equilibrium. Now, if the water is boiling, okay, what temperature should that be at? Well, it's undergoing a phase change. Liquid and gas phase change, it's water. The boiling point of this is 100 degrees Celsius, and if it is boiling, it is at 100 degrees Celsius. So the idea here is that I'm going to take my metal, leave it in the water. I don't want to let it drop to the bottom, because then the bottom of this is going to get heated by the hot plate, right? And my metal might get above 100 degrees Celsius. I don't want that. So I just want to have my metal just suspended in there. And I'm going to hold it and just kind of suspend it in that water for, I don't know, a minute, 90 seconds maybe, something like that, to get it up to 100 degrees Celsius, to let thermal equilibrium get reached between the water and the metal. Okay. Then, once this is hot enough, and once it's been sitting in there long enough, and I've got my temperature of my metal up to 100, I'll then take the hot metal out and transfer it into my coffee cup calorimeter, which will also have water in it at that time. Okay. Now, a couple things. We are transferring heat from hot metal to room temperature water. So, however much heat the hot metal is losing is exactly how much heat the cold water or room temperature water should be gaining. So we need 2 Q equals mc delta T equations. We need one for the metal, having lost heat, and one for the water, gaining the heat. Now, the end goal, eventually, is to solve for the specific heat capacity of metal. And in order to do that, we first have to know how much heat the water gains. So, Q equals mc delta T. I need to know the mass of my water inside these cups. I need to know the specific heat capacity of my water, which I do, right? Now, spoiler alert, we're going to be using joules today and not calories. So when we try to calculate this, and I'm calculating for the specific heat capacity of water, using the specific heat capacity of water, I want to make sure that I'm using the joules version of that. So the specific heat capacity of water in today's lab that you need to use is 4.184 joules per gram degree Celsius. Okay. So I know the mass of my water because I'll take the mass of it before I put it in the cup. There's nothing in here right now. Okay. But I will take the mass of my water using my balance back here. And then I will take, I'll use 4.184 as my specific heat capacity. And then I will take an initial temperature of the water. Okay. I'll go like this. Take an initial temp of the water. Read that, whatever that might be. Record it. And then I will transfer my hot metal, and it is boiling now. That's good. I'll submerge my metal, get it nice and hot, minute, 90 seconds, 2 minutes, somewhere in there, just to make sure it's reached thermal equilibrium, and it's 100 degrees Celsius. I'll take this, I'll transfer it in here, I'll cover it, and I'll allow the heat transfer to occur. Now, while that heat transfer is occurring, right, my temp's going to go up a little bit. That's fine. I just want to read it when it stops, once the metal and the water are now at the same temperature. So we need a second thermal equilibrium to be reached over here. And once that happens, I'll take a final temp, and now I'll have 3 of the pieces for water's Q equals MC delta T, right? I have the mass of my water, which I'll take from the balance. I have the specific heat capacity of the water, which is 4.184 joules per gram degree Celsius. And I have the change in temperature. I took an initial temp before I transferred the hot metal, and I take a final temp after the hot metal and the water have reached thermal equilibrium. What that does is that means I can now solve for Q of water. The Q of water will be positive because heat is going into the water when I put the metal in there. Okay? And I can then, so if I know the Q, I'm sorry for the weird cut. If I know the Q of water, I can then take that value of Q, which is positive for the water half, flip the sign, because it would be negative for the metal, and use the negative value of that heat for my metal equation, which is still Q equals MC delta T. So I'll then have negative Q, whatever that might be, we have to solve that from the water part, and I will have negative Q equals MC delta T of metal. M of metal, I'll also record. I'll take the mass of all 4 of these unknowns over on the balance. And specific heat capacity of metal is what we're trying to solve for. And the temperature change of metal will be final minus initial. Now, the final temp is going to be the exact same final temp we had for water. It's the same final temp between both of them because we're having a heat transfer occur, right? The initial temp of the metal is what it was in the water, 100 degrees Celsius. So we're going to hold our metal in the water to get it up to 100, transfer it into the cold water in the calorimeter, and allow a heat transfer to occur. The final temp of both is the same. Okay, the final temp of this mixture is the same for both metal and for water. So initial temp is really, really high for the metal. Final temp will be much, much, much lower. So as a result, you'll have a negative value for your temperature change, but that makes sense because we're supposed to have a negative value for Q for the metal because it's losing heat. Now, plugging all that in, you can solve for the specific heat capacity of your metal. Once you have the specific heat capacity, let me go to my computer for just a sec. Okay, I have posted a PDF of this. The first slide of the PDF is showing you the specific heat capacities of random metals. Okay, the 4 unknowns are on this list. All right, so once we have that calculated and you take the data that I'm going to provide you and you solve for the specific heat capacity of the metals, you should be able to solve for that and compare it to this list. Now, this lab doesn't give phenomenal data. It gives okay data. And I just ask that you try your best to take a look at the list, see what we get from our data, and try to make a comparison. Okay? We'll see how the data turns out, and I'll give you maybe some warnings if we need to warn you about some poor data. But anyway, so that's the whole lab. All right? I'm about 10 minutes in. What I'm going to do is I'm going to start setting this up. I'm going to start taking my masses, doing my data, all that good stuff, and then I will come back, provide you the data. All you're going to need to do is do these calculations. I'm going to need to see the calculations for A, B, C, and D, and then I'm going to need to see for specific heat capacity for those 4, right? That's like the end goal of those calculations. It's the specific heat capacity of the metal. And then last but not least, I want to see your guesses for what are they, right? Based on the specific heat capacity we calculate, what is that metal? All right. So you can also use your context clues, right? What I'm trying to say there is I'm telling you this first one, okay, is really, really dense. It's a grayish silver. Sorry, hold on, let me go back to full screen. There we go. It's grayish silver, and it's really, really, really heavy, okay? The second one is a shinier silver and really light, actually, for a metal. Really, really light. The third one is a medium density, pretty heavy, I guess, but it's all rusty, okay? And the third is also grayish and less dense than that first sample. So some context, obviously you can make better guesses or more educated guesses with your metals. Hopefully that helps too. But anyway, so let me get this going. I'll be getting some things going. I'll show you at least one trial of me setting this up and going through it. But you know, we'll give you the data and you'll have some calculations and then you'll turn those calculations in and that'll be it. Okay, so let me run through one of these trials with you and just show you how it's all going to work. Okay, so I have now in my coffee cups some water. Okay, and I've taken the mass of that water and I've got it recorded down here. I'm going to first make sure that I get an initial temperature because, again, it doesn't want to stand up nicely. That's okay, that'll work. I'm going to take an initial temp. Okay, I gotta let that kind of stabilize and get it just, you know, again, it needs to reach thermal equilibrium, right? I'm going to take this metal. I'm going to submerge it. I'm just going to dip it in the water and I'm going to suspend it. Again, I don't want it touching the bottom because the bottom of this beaker is going to be much hotter than 100 degrees Celsius because the hot plate is hotter than 100 degrees Celsius, right? The only way I can make this water boil is if my hot plate's above 100. And if it's just touching the bottom of the beaker, then I no longer have 100 degrees Celsius metal. I probably have above 100 degrees Celsius. So we're just going to suspend it like this. I'll let it sit for, I don't know, a minute, give or take. That should be long enough for the metal to reach thermal equilibrium with the boiling hot water, the 100 degrees Celsius water. And we'll give it a little bit longer here. I've got my initial temp. My initial temp is 22.4. 22.4. Okay. And let's see. That's probably good, give or take. So now I'm going to transfer my hot metal into my calorimeter, and I'm going to recap it and put the thermometer back in to get the total thermal transfer between the metal and the cold water in the cup. Here we go. Up and over and in, and I close the lid. I put my thermometer back in, and now I give it a little swirl just to kind of make sure that the water and the metal are coming into complete contact with one another. And then I kind of watch it. See what it does. Still moving up just very, very slightly. Oop, I just spilled. That's not good. That'll throw off the data. And I think it's stopped. So it doesn't take too long, okay? And the metal doesn't move the temperature of the water very much. The water-specific heat capacity is really, really high, right? So even though that's 100-degree metal I'm putting in there, the temperature of the water has literally gone up like 2 degrees. 24.2 is the final temp. And don't worry, you don't have to record that. I'll give you all that data in a data table. But yeah, that's it. So I'll do this 3 more times. Okay, I have B, C, and D, and the same process. The process is the exact same. I need to get the mass of my water from the balance. I need to take the initial temperature of my water using the thermometer. I heat up my metal to 100 degrees Celsius. I transfer the metal over and allow the heat transfer to occur, and then get my final temperature as well. So let me get all that data for you. I'll come back in just a little bit, give you a nice data table to run down everything we need to know, and then, yeah, you can do your calculations and turn it in, and that will be the lab. All right, so I've got all the data. Let me kind of give you this. This is what I posted on It's-Learning. This is a PDF, kind of a 3 little page outline. The first page here is what you're going to need to use to reference the specific heat capacities of these other metals. So try to find, again, where the data lines up with the other unknowns so we can kind of figure out what we have. We also have further down, this second slide is just how to do the lab. Obviously, I did the lab, not you, but I should say, sorry. Dylan and Kayla helped me with the lab, so maybe they kind of did the lab. But for the rest of you, you didn't do it. No offense. I'm not trying to be mean. But this is just describing how you should do the lab. You don't really have to acknowledge that one. But the third page here is all of your data. Okay, so I have our four unknowns: the mass of the water for each trial, the initial temp of the water, the final temp of the water, mass of the metal, initial temp of the water or metal, final temp of the metal. And now the final temps are the exact same. Do I really need two columns? No, not really, but I left it, okay? So what I'd like you to do then, and what I want you to turn in, and what you are required to do as a part of turning in this lab, okay? You need to show me the Q equals MC delta T equations for the water and the metal of all of these. Okay, so it's kind of like 8 math equations. You need to solve for Q of water first, which is positive. Flip it to negative, and then use the negative value of Q for the metal, and solve for the specific heat. Okay, you need 4 specific heats, one for A, B, C, and D. And then, after you have the specific heat capacities of all 4 of these unknowns, I need you to reference this chart and try your best. Okay, now I can tell you none of the numbers are perfect, so they are all off by a margin of, I don't know, a decent amount. But between looking at them, right, when I've kind of shown you in the camera earlier in the video, if you need to go back, you can go back. Between looking at them and making an observation that way, and even using the specific heat capacities, like they're close. They're pretty darn close. The one thing is C and D are really close together in terms of their specific heat capacity. The good news is C is higher than D, and that's also true on the actual table, on the chart. Okay, so C should have a higher specific heat capacity than D. They're very, I think they're literally separated by like 1,000 when you do the math and you crunch all the numbers. But C should be a higher specific heat capacity than D, and pick the one that's closest. Okay? So, that is all I have. Have a lovely day. Please turn this in if you could by today. That would be great. Obviously, whenever you're watching this, turn this in after you're done. Again, what do you need? Turn in a piece of loose leaf paper or a separate piece of paper with the math. I need 8 Q equals MC delta T equations, 4 for the water for each trial, 1 for the water in each trial, which is 4, 1 for the metal in each trial, which is 4, so 8 total. I need the specific heat capacities of the metal, because that's the end goal, right? 4 specific heat capacities of metal. Please make sure you are using joules. Okay? The chart I gave you right here is in joules. So please make sure you're using 4.184 joules per gram degree Celsius when you do the math for the water. And then 4 answers, right? A is blah, blah, blah. B is blah, blah, blah. If that makes sense. So thanks, guys. Have a lovely weekend. We'll catch you on Monday, and stay warm.